Hello and welcome to Scientists in Action Climate History According to ICE. I'm your host, Kate, from the Denver Museum of Nature and Science, where we are not joining you live today, but instead we are here at the National Science Foundation Ice Core facility. This is a really cool chance to see a little bit behind the scenes, as well as meet an amazing scientist who has some incredible knowledge to share with us. Before we get started with today's program, a couple of things I want to go ahead and take care of is one, if you are going to be our on-camera school, we're going to ask that you stay off camera and muted until we call on you for our open Q&A in about 15 or 20 minutes. If you are not on camera and you have questions, love it. We have an open chat for that. So teachers, students, however you have your computer set up, feel free to post questions in that chat throughout our program, and we can make sure that Richard gets them. So to that note, I would like to introduce Richard, who's a curator here at the Ice Core facility. Richard, what would you like to tell us a little bit about yourself or maybe your job here at the facility?
Yeah, so my name is Richard Nunn. I'm the assistant curator here at the National Science Foundation Ice Core facility. I've been working here for about 13 years now. And we're just going to kind of have a little brief chat today about what it is that I do, sort of what my everyday job entails. We'll discuss a little bit about the logistics of how we go to these remote places like Antarctica and Greenland and drill these ice cores and safely bring them back. And then we'll dive into the actual science of ice core research, what it is that we can learn from studying them and why it's so important to us. But before we do that, I think we have a question for you guys.
We do. So if we could go ahead and get that poll pulled up. Teachers, students, we want you to think about, why do we study ancient ice? Is it because it could tell us perhaps about things in the past, things that have happened from volcanic eruptions to maybe things that lived before us? Could it help us predict the future and where our climate's going? Is it because it's just interesting, or maybe it's a combination of all of them? So teachers, students, go ahead and post your vote in the poll, and we'll see what you think. All right, take about 3 seconds more and place your vote if you haven't already. All right, and let's close that poll and see how our audience fared. Wow, across the board, looks like everyone says it's all the above. Looks like that might be our answer for today.
I think so.
You? Is that the answer, Richard?
That is definitely correct.
Nice.
So, cool. So, this facility is very unique. This is actually the only place like this in the United States. We basically are the central repository for all of the ice cores that have been drilled by the U.S. polar programs over the last 60 years or so, since the mid-1950s. So currently our collection contains about 23,000 meters worth of ice, all stored in these wonderful silver tubes like what you see here sitting next to me here. So I have 23,000 of these things filled with ice that I have to keep track of and keep cold as well. So a big aspect of my job is to keep a detailed inventory of everything that's in these cores. When the ice comes back to us from the field, typically it is in a single meter long cylinder like this, and we will then run them through what we call a core processing line, where we cut the ice into various different sticks or chunks that are going to go out for analysis or go back into our archive. So as you can see here, when I open up one of these tubes, there is not a single cylinder of ice in there anymore. Rather, it's all of the remnant archive pieces. I'm keeping track of something like 200,000 individual pieces of ice. But I have a digital database that allows us to know exactly where everything is and where it came from. So when a scientist wants to put in a proposal to access part of our collection, they can go online and see exactly what we have available and use that to request samples. And once that gets approved, then I will spend some time in the freezer, usually cutting the ice for them, packaging it into these insulated shipping boxes that we have, and then sending it off to the university where they're actually going to do the research and analysis on the ice cores. As you can imagine, to collect these things and bring them back to our facility is no easy feat. Going to some places remote and cold as Antarctica is an awful lot of work. The logistics are quite involved. In general, the U.S. Has a handful of permanent bases in Antarctica that are occupied year-round. But most of this deep field work we're doing, such as where we go collect these ice cores, we have a very limited window of time in which we can do this. Basically during the summertime in Antarctica, which makes our field season run from about November until the end of January. So we have 3, maybe 4 months if we're lucky, of decent enough weather to actually go and work on the ice to drill these ice cores. For the most part, the U.S. stages everything out of a station in Antarctica called McMurdo. It's a little base that's located near the coast, that actually used to be a military base many years ago, but as part of the Antarctic Treaty, no country is allowed to have a significant military presence in Antarctica. So they converted this to a civilian base, and it basically acts as the jumping off point for all of our deep field research. So we will generally fly our folks out to New Zealand, which is not too far away from Antarctica. And then from there, we will load them onto one of these LC-130s so they can fly out to the field site. These LC-130s are aircraft that are run by the 109th Air National Guard, and they were modified very specifically to work on the ice sheets of Antarctica and Greenland. When I say modified, I basically mean they stuck skis on them so that they could actually land out on the ice sheet. So we have a wide variety of cores in our collection from these different field locations. A lot of them were a relatively simple project, maybe one season, drilling a few hundred meters, bringing it back. But there's a handful of cores in our collection that are significantly deeper than that. In some cases, we drilled over 2 miles of ice from a single location. The deepest and oldest core in our collection comes from the Vostok ice core that was drilled in East Antarctica back in the mid-90s. They drilled this core to a total depth of about 3,600 meters, and the ice that they dated at the bottom of that dates back to about 420,000 years ago. It happens to be the oldest continuous core that we have in our collection. However, the Europeans drilled a core not too far away from there called Epica Dome C, which is currently stored at the University of Copenhagen. And that one was dated to 850,000 years ago. To date, that is the oldest continuous ice core that's ever been recovered. But we have the pleasure of having the oldest ice known to man in our freezer. There was a project at a place on the coastline of Antarctica called the Allen Hills Blue Ice Field back in 2019. They drilled some ice in this region where ancient ice from the interior of Antarctica had migrated to the coast, and rather than breaking off as icebergs as it normally does, it got stuck. And it just sat there and folded over on itself, exposing this incredibly ancient ice at the surface. So we didn't have to drill through 2 miles to get this old ice. Rather, we were able to collect it from just a few dozen meters below the surface. And this ice recently was dated last year to roughly 4.2 million years old. So while it is not a continuous record, it is the oldest ice in the world that's just living in our freezer right now. You can imagine that drilling a deep core like this isn't an easy prospect. And in fact, most of these deep cores, when they're drilling below 3,000 meters, they take multiple field seasons to recover. One of the most recent deep ice cores that the US drilled was called the Western Antarctic Ice Sheet Divide Core, or Waste Divide for short. This was drilled between the years of 2006 and 2012. So it took 5 actual seasons of drilling in order to recover this core. Like most of these deep projects, the first season was actually just setting up the camp, getting all of the infrastructure put in place in order to support this project for the foreseeable future. And again, because we only have this narrow window of about 3 months, we're limited in the amount of ice that we can drill. On top of that, one of the issues that we have in these field camps that we work in during the summer and then abandon during the winter is that slowly but surely everything gets buried in the snow. So whenever they would get back to the field in the following summer, the first couple of weeks were generally spent digging everything out of the snow and then getting camp up and running before they could even start drilling. So if we're lucky, on a good field season, we could recover maybe 800 meters to possibly 1,000 meters of ice. So not only are we limited in the amount of time that we can spend in the field, but the drilling process itself also takes a long time. I have an example of an ice core drill here for you. Most drills are going to be somewhat similar in design. They're going to have these tungsten carbide teeth attached to this drill head that they can use to very slowly grind their way through the ice. And attached to the back of that drill head will be a barrel that can vary in length. The one I'm holding here is just under 1 meter long and was part of a smaller project that was most likely a hand drill. But for some of these deep ice cores where we're drilling thousands of meters into the ice sheet, they'll have much larger setups. This is the disc drill here, the deep ice sheet coring drill that was used at Waste Divide. They were able to drill about 3 meters of ice at a time with this. Once they drilled that 3 meters, these things called core dogs that were in the actual drill bit would engage and grip the ice, and using a little over 1,000 pounds of pressure, they could snap that ice off at the base and then bring that entire 3 meter section up to the surface. So the actual drilling time to drill that 3 meters usually took between about 45 minutes and an hour. But then you have to factor in the travel time in terms of how long it takes to get the drill down to where the ice is and then bring it back up. To give you sort of an understanding as to how long this takes, the deeper you go, when they were in the last year of the Waste Divide project, below 3,000 meters, it was a roughly 5-hour round trip just to go down and drill 3 meters of ice and bring that back up to the surface. Once they would do that, they would take that 3 meter section of ice and they would push it out of the barrel and into a room where they have the people set up to measure the depths of these cores, cut them into more manageable 1 meter long pieces, and then pack them into the tubes that were going to be used to ship them back to the States. Once they got these things packed up and all of the depths had been registered, everything had been punched into a database, they would then pack these tubes into what we call insulated shipping containers. They're these boxes that have these extra thick layers of foam around them, and they could then palletize those in order to ship them back to the US. And near the end of the field season, they would take all the pallets of these boxes of ice that they had generated, and they would load them onto one of those LC-130s for its final flight out of camp. And they would do what's called a cold deck flight, where they turn the heat off in the cargo area of the plane, keeping the ice plenty cold while it's traveling from the field back to McMurdo Station. Once they get to McMurdo, they have these specialty containers called safe core containers that they would store the ice in. And these things are basically very large shipping containers that are insulated and have a redundant generator system on them. And they can cool the inside of these down to about minus 35 degrees Celsius. So they cool these things down, they leave them sit there, and then near the end of the summer field season, the final container ship would arrive at McMurdo Station to bring a whole lot of supplies back to the States. That included our 3 safe core containers that had our ice in it. They would load those containers onto the ship, plug them into the ship's power source, keeping them at minus 35 for the roughly month-and-a-half journey from McMurdo to a place in California called Port Hueneme. Once they got to the port, they would offload these containers, put them onto a flatbed truck, and then kick those generators on to keep them cold and drive those containers out here to our lab in Denver, where we would then offload the ice and stuff it into our back freezer, where everything is kept at a balmy minus 38 degrees Celsius. Once we got the ice stored into our freezer, unpacked and put onto our shelves, we would then plan for what we call the core processing line, which would take place over the summer when all of the different universities involved with this project would send a small army of graduate students to our lab. And we would spend anywhere from 2 to 4 months in the freezer processing all of this ice. And basically that means that we would take every single meter out, double check all the depth measurements, and then run it through the series of saws that you see here to cut out the various sticks and blocks that are either going to go out for analysis or go back into our archive. While we're doing this CPL, we might have upwards of a dozen people working in here, everybody standing at their station. And when we really got up and running, we could process about 40 meters of ice a day. And you can imagine how much fun that is when we're working in the exam room, which is kept at a slightly warmer minus 24 degrees Celsius, which is about minus 10 degrees Fahrenheit. So we would spend 8 hours a day in this freezer, cutting all of this ice into all of the sticks that were going to be analyzed for the science that we're doing on these ice cores. So you may ask yourself, what is it that we're studying these ice cores for? Why are we spending all of this time and resources and energy to go literally to the ends of the earth to recover these things? And in all honesty, there's a lot of really cool stuff that we can learn from studying ice cores, but the main driving source for this is to understand our climate, specifically how our climate has changed in the past. Ice cores are, simply put, the best record of the Earth's climate over the last 850,000 years. There's a lot of reasons for that, but a big part of it has to do with the fact that ice cores are the only source we can go to on the planet to get an exact measurement of what the atmosphere was like tens of thousands or hundreds of thousands of years ago. As the snow is falling on these ice sheets of Antarctica and Greenland, they have air kind of moving between these snowflakes. As it gets buried deeper and deeper, that snow gets compressed more and more. And by the time you reach about 100 meters beneath the surface, the pressure is so great that that snow is finally compacted into solid ice. And at that point, any of the air that was moving through it becomes trapped. And so we can then go and extract these ice cores and literally get a measurement of what things like carbon dioxide or methane may have been like thousands of years before humans were around to measure these things. The other aspect of ice cores that's really useful for understanding our climate is that they have a really good record of the Earth's temperature. And that is studied by looking at what we call the stable isotopes of the water molecules that make up the ice. Basically, we're looking at the hydrogen and oxygen, that wonderful H2O that makes life possible. And essentially, there is what we would call normal water and heavy water. Heavy water comprises isotopes of hydrogen and oxygen that simply have more mass. And the ratio of these heavy atoms to the normal atoms is very heavily temperature dependent. So by studying the physics of these isotopes and the nature at which they represent temperature, we can go back in time, look at these ancient isotopic signatures in the ice cores, and determine what the temperature was at the time that snow fell thousands and thousands of years ago. And then, of course, time is an important aspect of this too. If we couldn't date these cores, then none of this other information that we've extracted from them would really mean a whole lot to us. So for the dating methods, there's a few different ways that we can go about this, but in general, it has to do with the fact that there's noticeably different chemical signatures within the snowfall on these ice sheets during the summer versus during the winter. And this primarily has to do with the presence of ice, sea ice. If you imagine around Antarctica during the wintertime, when it's dark for several months out of the year and it's incredibly cold, the sea ice grows around Antarctica, and it blocks a lot of the ocean chemistry from falling on the surface of Antarctica with the snowfall. On the other end of that, in the summertime, when the sea ice melts, a lot more of that ocean chemistry is actually being incorporated within the snowfall. And so when we do our continuous chemical analysis of these ice core sticks that we've cut out, we can see these chemical signatures rising and falling and rising and falling as we move from summer to winter to summer to winter. And so we can use this to, kind of like tree rings, essentially count the layers of ice and determine how old it is that way. This can also be verified with a machine that we call the electrical conductivity machine, which is kind of what its name implies. It's testing the conductivity of the ice itself. It's running these electrical probes over a nice flat surface of the ice and seeing how well electricity flows through it at different points. The idea here being that these layers that have a higher concentration of these chemicals, more salt from the ocean, more dust, they are going to conduct electricity better. And so we will have a high peak in that conductivity, and then it will drop during these the other season when you don't have as much of that material in the ice itself. And so we can run the ECM over the ice, and we can do our chemical analyses, and we can essentially count these layers to give us a continuous date from the very surface all the way back to, in some cases, 3,600 meters below the surface. And then this can be triply verified when we find volcanic layers in the ice, which is actually quite a common sight. The Race Divide core that was 3,400 meters had something like 150 or so volcanic ash layers. Most of the time, these layers are barely visible. They're very faint. They're about as thin as a pencil line, but we can extract material from them and look at the chemistry of those volcanic layers. And in doing so, we can tie that back to the very specific volcano that caused this ash layer to be deposited on Antarctica. Every volcano in the world, when it erupts, it has its own unique chemical fingerprint. So it allows us to tie these layers from the ice cores to the actual volcanic event. And then we can use a method called radiometric dating to get an exact age on that volcanic material and tell us exactly how old we are in the ice core. And in doing so, that can verify this continuous dating that we have by getting these pinpoints in time based off of these ash layers. So then we can take all this information and put it together and kind of start to piece together what our planet has been doing over the last few 100,000 years. We've looked at the atmospheric gases that are trapped in the ice. We've recreated the temperature using the isotopes, and we've dated the ice cores. And when we put all that information together, we do what us scientists like to do, and that is to make a bunch of squiggly lines on a graph and then try and interpret what those mean. In the case of the ice cores, we're generally looking very specifically at the greenhouse gas levels in our atmosphere, carbon dioxide and methane, and how our temperature has changed. And what we see is that over the last 850,000 years, there has been somewhat of a regular pattern. We get these periods that last about 100,000 years where temperatures on Earth, on average, are about 8 degrees colder than they are right now. And the CO2 levels in the atmosphere during that time hover right around 200 parts per million. So things will start to warm up. Over a couple of thousand years, temperatures will warm by 8 degrees. These ice sheets will retreat a fair amount, and CO2 levels will go up to about 280 to 300 parts per million. And then we'll get this stable period that lasts about 10,000 years before things cool back off again. This is what we call the glacial and interglacial cycles of the ice age. We entered in the most recent ice age about 2 million years ago and are smack in the middle of it right now. We just happen to be in one of these nice warm interglacial periods. If we were to go back to one of the glacial periods when temperatures were 8 degrees colder than they are now, just to give you an example of what the Earth would have looked like, places like New York City would have been under nearly a mile of ice during that time. So we've been able to use these ice cores to get a really good understanding as to how the climate has naturally varied over the last few 100,000 years. And then we're looking at our modern times and trying to figure out what to expect moving forward because something very significant has changed. When we look at the ice core record, we never see CO2 levels rise above about 300 parts per million. And in the most recent time, until the pre-industrial era, CO2 levels were hovering around 280 parts per million. As of this year, we are now sitting at 425 parts per million. It is significantly higher than we've ever seen in the ice core record. And typically the kind of time that it takes to increase CO2 levels by 100 parts per million is in the order of a couple of thousand years. We've done that in less than a century. We have increased our CO2 levels by nearly 140 parts per million, most of that in the last 50 years. And we very much know this is due to human activity. We can trace back the excess carbon dioxide and excess methane in our atmosphere to humans burning fossil fuels and a variety of other activities, including agriculture. So the big question that now comes up is, we've increased these greenhouse gas levels by a significant amount in a very short period of time. What is that going to mean for our climate and for our temperature? And it's kind of a difficult question to answer, because with complex systems like our Earth's climate, normally when we see something change like this, we want to look to the past and see, how did it react the last time this change happened? But this change has never happened before. We are in unprecedented territory. So in order for us to really understand and predict what we can expect to happen with our climate over the next decade, 50 years, century, it's really important that we understand how all of these factors behave in a natural environment. So the ice cores give us that record. It allows us to study the dynamics of how climate change naturally happens, and then use that information to build these computer models and these simulations that can recreate what happened in the past, and then use that to model what's going to happen moving forward. I'm always a fan of saying that the key to the present is understanding the past, and ice cores are the best record we have of our past climate. And by using those and understanding them and then modeling our future moving forward with that ice core data, we can have a better understanding as to what we can expect to see in terms of climate change over the next century, and hopefully what we can do to, if nothing else, prepare for these changes, or in some cases mitigate the worst of them. So the ice cores are incredibly important for understanding the past, but also understanding our current moment in time, and what humanity is doing and what we can do to course correct. So I'm very fortunate to be able to work in this community with all of these brilliant scientists that have been doing all of this work for decades to understand what ice cores can tell us about our
planet. What a testament to amazing scientific feats. It sounds like this is a huge process. You mentioned spanning across the globe. Folks are collecting these and transporting them and processing them and making sense of the data that they're communicating with us. And it also sounds like, to understand climate history and climate change, it takes a bunch of different kinds of science disciplines, whether it's chemistry or geology or physics or, something in between, or none of those. There's a lot of people involved.
Absolutely. There's a lot of interdisciplinary science that goes into this. Ice core science is a big umbrella term, and there are so many different types of scientists underneath that are necessary to essentially learn how to translate what these ice cores are telling us and make sense out of them.
So you, in a sense, you kind of have this really important job that's like in between a lot of these fields, right? Where you're not necessarily processing this data yourself, but you are facilitating it so that scientists across the world can gain access to the knowledge stored inside these really, really, really old tubes of ice and make meaning of it, correct? That's right.
That's right. I'm basically a librarian, and my books are ice, and it takes a special kind of person to be able to translate the language that these ice cores tell us. But with all of these brilliant people working together, we're able to essentially read the story that the ice cores tell us about our planet. And it's just absolutely fascinating what we've been able to learn.
Incredible. So, I feel like I have to ask, because I'm sure a lot of our friends are, thinking about the window behind you and stuff. What is it like to work here? I'm sure it's cold.
It's very cold. So our freezer is broken into these two segments. As I mentioned, the exam room is minus 24 degrees Celsius. That's where we do most of our work because it's a little bit warmer. And our main storage is about minus 38 degrees Celsius, which is minus 36 Fahrenheit. So clearly we bundle up when we're working in there. We have all kinds of really great polar gear. That being said, a lot of the work that I have to do requires a fair amount of dexterity. And so I can't really wear the big, heavy Antarctic mittens. More often than not, I'm wearing what amounts to kind of glove liners, if you will. And then, of course, I'm touching this incredibly cold ice while I'm in there. So normally after about 30 minutes or so, I usually have to take a break and step out here in the room that we're sitting in and use my best friend in the world, this little hand dryer over on the wall there, to defrost my hands and defrost my glasses.
How do you know where to cut the ice? I think that's like another burning question I personally have.
Yeah. So especially with these deep projects where we're talking about, 5 years worth of drilling and millions of dollars going into it, there's usually going to be anywhere from 8 to 12 universities that are involved in this project. And so before we even set foot on the ice sheet and start drilling this core, they will get together and determine how they want to divvy the ice up. This is a good example of how the Greenland Ice Sheet Project core was divvied. This was what we call our cut diagram. But essentially, they would take this cylindrical core, and then they would come up with all of these different sticks to cut out of it, so we could send stuff out for the isotope analysis, send things out for the chemical analysis, which would be the isotopes that come out of the top. The chemistry comes out of these 3 by 3 centimeter sticks, and then they would cut these roughly 400-gram chunks out of the heart of the core to do gas analysis for methane and CO2. But then we would make sure that we're leaving about 2/3 of the core behind as archives, so that once the initial work is done, papers have been published, then future scientists can come and access our collection and basically refine the work that has already been done.
I love that you made that point, because I think that's one thing we often forget when we talk about science is, just because we have incredible technology now, doesn't mean we won't have even better, finer tuned technology in the future.
Exactly.
I know even from the museum, we look at a lot of the data that folks collected 100 years ago, and we are now reworking a lot of those same studies and finding more information from what scientists back then thought they'd already studied.
Absolutely. Yeah, as technology gets better and better, we get better ways of analyzing these cores. We learn new questions and then get new answers. A really good example of how technology has increased the amount of information we can pull out of these ice cores is that prior to 2006, when the waste divide core was drilled, when they were doing their isotope analyses, they would take a single stick and they would cut it into 5-centimeter chunks. And then they would analyze each one of those. So they would get 20 data points per meter for this isotope temperature record. The new system that is now used, that was developed by the folks at CU Boulder, is a continuous melter system that gets over 2,000 data points per meter. So the resolution of what we're looking at is incredible. And they've been using this to go back and reanalyze old ice cores that were drilled 20 or 30 years ago and get this really beautiful isotopic record.
So this is a relatively new study, and you were kind of talking about this earlier even. This is, studying ice cores is relatively new as far as science goes, and honestly, probably even talking about climate has become a bigger issue. But these data points that we're taking are really old, right?
Correct.
Can you remind me again how old we're talking?
In terms of the age of the ice,
Yes.
in some cases over 850,000 years old.
Wow.
Yeah.
So there's a lot of data for us to look back into to even make sense of the future moving forward.
Correct.
Very cool. That's incredible. What a neat opportunity, It must be really weird to hold something like this and think you have been frozen in time essentially for a really long time.
Yep, I've been doing this for 13 years and it still never ceases to fascinate me to pull out some of this ancient ice and just hold it in my hands.
Do you get nervous when you're processing ice? I mean, I can't help but think if we're trying to test the little air pockets, that minuscule bubbles of air,
Mhm.
if they escape, they're gone, right?
Correct.
So what kind of things do you have to safeguard against?
So one of the big things is, I will say, when I first started this job, I was always nervous cutting ice. I've been doing it long enough now, I'm comfortable, but a big part of that is because we have a lot of practices in place to reduce the chances of breaking the ice or dropping the ice. One of the things is we almost never pick the ice up. Anytime we're transferring it from one place to another, we will slide it onto a cart, roll that cart around the room. We try and minimize the actual handling of the ice. And in the time that I've been here, I have dropped one piece of ice. So I feel like I've got a pretty decent track record.
I was going to say, that's an amazing track
Yeah.
record. I feel like scientists routinely break things in labs. It
Yes.
just happens. It's a mess. Do your hands melt the ice and stuff too? Is that a concern?
No, partially because it's so cold in there, but also we're not handling it with our bare hands. So the amount of space between my hands, the glove, and then the ice itself, it's fine. We do have to be careful whenever we're using lights to actually look at the ice detail. We use LEDs because they don't put out that much heat, and we make sure that we don't actually contact the ice with them.
Like I said earlier, it sounds like there is a huge amount of work and consideration that goes into making sure this is happening as smoothly as possible.
Yep.
Well, at this point, I would love to invite our friends on camera from St. John's the Baptist School. We would love to have you unmute and join us on camera, and we cannot wait to hear what amazing questions you have for Richard. Meanwhile, as well, if we have friends who have questions in the chat, feel free to be posting those in there, and we can make sure we get those passed on too. Hello, we can see you. You'll have to, I'm gonna ask you to speak nice and clear and loud. We are not in a freezer, but we're very close to one, so our audio can be spotty, but can't wait to hear your questions.
Bella, right there. They're ready for you, right up here.
Does the weather have something to do with what type of clouds we will have like that day?
Yeah, so that's a really good thing to point out the difference between weather and climate. Weather is the short term and climate is these longer term trends. But we do need to understand how different weather systems can affect what kind of snow falls and what kind of signals that leaves in it. So for example, when we're out in the field drilling one of these ice cores, there's also people on the surface actively collecting samples of water vapor in the atmosphere, collecting fresh snowfall, doing all of the temperature studies, basically understanding how the weather of that day is affecting what we see at the surface, so that when we dig down deep into these ice sheets and we're recovering these cores, we can kind of have an understanding as to the weather that may have been involved with what was being deposited during that short period of time. And that gives us a better understanding as to the longer changes of climate, which is more over the terms of hundreds of years rather than just a few years.
Well, I think that was a great distinction. It's a
Yeah.
good reminder.
Yeah.
What other questions can we get from the classroom?
How can you tell how much carbon dioxide is in the bubbles in the ice?
Great question. So the way that they extract and measure these atmospheric gases is to take their sample, and generally what they will do is put it into a vacuum chamber of some sort. And for carbon dioxide, they can't just let the ice melt for the air to be released, because CO2 actually dissolves in liquid water. So they will put their sample into a vacuum chamber that is inside of a freezer, and then they use a variety of techniques. My favorite was described to me as a high-tech cheese grater, but they either crush or grate this ice up. That releases all of the gases that are in there. They can then pump those gases out through these filtration systems that can separate out the different molecules of air, and they run them through a machine that's called a mass spectrometer, which is basically using laser and wavelengths of light to bounce off of the molecules of air, basically, and they can identify what these molecules are, and that allows us to identify the concentration of things like carbon dioxide or methane.
Very cool. That was a great question.
That was a really good question, yeah.
Oh, I'm Andrew, and when you study the past from the ice, have you found a gas from back then that is no longer present today?
That is a super good question. So we don't find gases then that aren't present today, but what we do find is a lot of gases are very different in terms of their concentration. One that I can think of in particular is a very, very trace gas called ethane, that before humans were around, it was relatively stable. It really had nothing to do with climate. It just always was a constant background level, which is measured in parts per trillion. So it's very, very, very trace. And then ethane is something that is released through a lot of different human activity. So we see ethane levels nowadays are like orders of magnitude higher than what they were in the ice core record. So when we're looking at the gases trapped in the ice, it's the same stuff that exists in our atmosphere today, but the concentrations can be vastly different.
I think you were even mentioning earlier, there's certain events in human history, like something about the Romans and.
Correct. So not speaking on gases, but just other particulates that get into the atmosphere. You know, the air around the planet can carry very, very fine particles of all kinds of different stuff. One of those things is lead. And surprisingly enough, there was a group that was doing studies on these ice cores looking at lead concentrations, and they were pretty constant background. And then they were able to identify a spike in the lead in the ice cores when the Romans started smelting lead, back in whatever BC that was. And in more modern times, looking at some of these shallow ice cores, they can see when we started using leaded gasoline in our cars until we realized that was bad. And so we switched to unleaded gasoline, and those lead concentrations in the ice cores dropped again. So we can see all kinds of stuff that is basically mixed within our atmosphere and falls onto the ice sheet and is preserved. And it can tell all sorts of different stories, some of them about humanity.
Wow. We just have these incredible histories just frozen in ice, and we don't even think of it a lot of the time.
Yep.
So what a cool question. Y'all have amazing questions. We cannot wait to hear another one.
Weston. Paula, you'll be after Weston. Come on up here.
How much of pollution is trapped in the atmosphere in 1 year?
Pollution is trapped in the atmosphere in 1 year?
How much pollution is trapped in the atmosphere every year?
Gotcha. It changes from year to year, but we are dumping literally dozens of tons of carbon dioxide and methane into the atmosphere every year. I don't have that number off the top of my head, but it has been increasing pretty steadily for the last 50 years as population has increased and as our needs for energy, meaning we're burning more coal, we're burning more carbon dioxide. And the thing about that is we're measuring how much these greenhouse gases are increasing in concentration in our atmosphere. And it's only been recently that we also realized a lot of this is also being absorbed by our ocean. The oceans are a gigantic carbon dioxide sink. The CO2 will actually dissolve into the oceans, which causes the acidity rate to rise, which is why we've been seeing issues with a lot of the reefs and corals dying. So when we look at the amount of CO2 that's increasing in the atmosphere, that's only a percentage of how much excess we've actually put out, because a lot of that is also being absorbed by the ocean.
Very cool. Yeah, it just goes to show like how everything on our planet is super interconnected, whether or not it's, you know, on land, in the water, or in the air.
Yep, that's
getting
all
stuff
part
on
of-
ice. It's
Exactly. It's all part of the climate system.
all related. You know, there's plenty of chemicals that we don't have necessarily quite as many of in the air because humans have taken note and said, ooh, those are not good. We don't want those.
Yep.
And we've been able to get rid of those.
Yeah, a really great example of the world coming together and realizing, hey, this is bad, was when we discovered that the ozone layer was developing a hole, actually over Antarctica, interestingly enough. And scientists were able to trace it back to these chemicals that we call chlorofluorocarbons, CFCs. And so a whole bunch of countries got together and they signed something called the Montreal Protocol, and it basically banned the production and use of these CFCs. This was probably 30 years ago.
It was in the 80s.
And we've seen that hole in the ozone layer has started to repair itself, and it's almost back to normal now. So it is possible for humans to come together and realize that we're polluting the planet in ways that we shouldn't and course correct.
Just goes to show too, we're very small in like the grand scheme of climate and earth and all of that. So cool. What other questions do you have? St. John the Baptist.
What if the Earth's greenhouse gases were to get colder? Would it affect human society, or would it help human society and Earth?
That is a great question. So getting colder would be like if we were to drop back into one of those ice age periods or glacial periods, the ice advancing and covering a lot of our places like New York in a mile of ice wouldn't be great. But the thing is, if we were to reduce carbon, if we figured out a way to remove CO2 from the atmosphere and actually drop it below where it was during the interglacial, that level of change would still probably take place over a very long period of time. In general, the planet being a bit warmer or a bit cooler in and of itself isn't necessarily a bad thing. The concern is that when those changes happen quickly, it causes a lot of these ecosystems that we rely on to be under a lot of strain. That's what causes animal extinctions. It causes these droughts. It causes our agriculture to move. So warming or cooling in and of itself isn't a big deal. If it takes place over a couple of thousand years, we can adapt to it. But if we see the kind of changes that we're seeing now, the rapid climate change of warming, that is not very good for humanity. And if we saw that on the other end, if there was something on the planet that caused us to cool off as rapidly as we seem to be warming right now, that would cause an equal level of strain, but for different reasons.
Have we had instances where the planet's kind of cooled rapidly before? Or?
Yeah, not in a significant amount of ways, but there's a particular event that the ice core records shows that there's still a lot of questions in the ice core community about. It's called the Younger Dryas event. So the planet started warming up from its last glacial cycle about 12,000 years ago, more like 11,000 years ago. And it was warming along a trend that seemed quite natural. And then all of a sudden, temperatures dropped by about 2 degrees Celsius over the course of a couple of decades, which was incredibly fast. And then everything kind of course corrected and the planet warmed back to the interglacial cycle as if it was supposed to. There's still a lot of question as to what caused that sudden rapid cooling, because that was clearly before humans had any sort of influence on the climate. We were still nomadic people at that time. The main theory is that something happened where, because things were warming up, the Greenland ice sheet collapsed and a whole lot of it melted. And we basically injected, not we, but the planet injected a whole lot of fresh water into the North Atlantic, which desalinated the North Atlantic, allowing it to freeze easier. And that injunction of cold water may have shut down the Gulf Stream, which is a huge reason why we have the climate that we have right now, as the warm water from the Gulf of Mexico is then carried up over Northern Europe. And if that conveyor belt essentially was shut down even for a decade or so, that could have been what caused that really rapid drop in temperature.
Wow, everything is so interconnected.
Yeah.
It's amazing. What amazing questions y'all are asking and leading to so many great other questions. Thanks. What other questions can we snag from the classroom?
Jada. And Ginger after Jada.
Could the climate change how we live our everyday lives?
Did climate change help our everyday lives?
I think just change how we.
Or
live
just
our
change how we live
everyday
ours?
lives.
Yeah. Yeah, I mean, I think in order to really address the impact of climate change, we do need to change our everyday lives. We have to, as a society, start to learn how to more rapidly move away from the fossil fuels that are causing all of these excess greenhouse gases in our atmosphere, move towards more renewable energy to power our grids and power our transportation. There's always going to be a place in the world for fossil fuels, but it needs to be a much, much smaller place than what it is right now. So if we as a society can recognize the threat of climate change as it is and slowly move away from the causes of it, I think that would improve everybody's lives. And eventually these new energies are going to be creating a lot more jobs and bringing a whole lot more money into our economy as well. But a lot of that requires technological innovation. Some of the green energy just isn't there yet. It's not as efficient as digging up oil and burning it. So if we can innovate and come up with better solutions for renewable energies, that's going to benefit everybody.
Humans are pretty resilient, so we are very curious and good at learning new things.
That's right.
I think, and we'll see a lot of changes in our future, and some of them could be pretty positive ones.
Absolutely.
So,
Fingers crossed for nuclear fusion and not the bomb type.
very good. All right, let's get one last classroom question. I think we have one queued up.
Other than cars and factories, what else can cause pollution?
That's a really good question. So yeah, cars and factories are a big part of that. Manufacturing uses a lot of water and creates a lot of carbon emissions. But there's also agricultural sources of this. One of the biggest producers of methane is actually rice paddies, which we don't think a lot about here, but so much rice is grown to feed the massive population in Asia. And rice paddies are basically in these kind of wetlands. And they're kind of like the rice plant itself is almost like a straw. And when you're growing this rice, it actually takes a lot of methane that has been kind of trapped in these wetlands, and it sort of pumps it out into the atmosphere. And so as we've increased our rice production to feed a growing population, the amount of methane that is being produced by these rice fields has increased significantly. Other forms of agriculture as well. You guys have always probably heard people talk about cows. It's actually not cow farts, it's cow burps that release a lot of methane. But with the sheer number of cattle that we have to raise in order to feed our population, there's an awful lot of methane being produced by them as well. So yes, there's manufacturing and there's cars, there's burning of oil and burning of natural gas, there's heating of our homes, but there's also a whole agricultural component to this that also releases a lot of greenhouse gases.
There's a lot of things to look at and ask questions of and think, how can we diversify or just, do things in moderation?
Exactly.
So, well, we are running out of time. So is there anything, Richard, you would like to leave the kids with today, as far as maybe how they could pursue something like this, or just a general message of science that you want to convey?
Yeah, if any of you are interested in this kind of science, whether it's specifically ice cores or just the kind of environmental science that we do, there's a lot of pathways to get there. In all the years I've worked here and all the scientists I've worked with that do ice core research, most of them started their college careers in some kind of environmental science background, whether it be geology, which is where I got my start, or chemistry, physics, atmospheric chemistry, climate change, various different things like that. There's a lot of initial starting points. As you get further into your university education, if that's the path you decide to take, graduate school starts to narrow things down a little bit more. So in terms of ice core research, somebody working on a graduate degree might be specifically focused on researching just one core, or looking at just the greenhouse gases, or figuring out better methods of refining our dating techniques for these ice cores. And then when you get to the final top tier of that, for people that are doing their PhD, At that point, they're going to be very narrowly focused. They're going to be just doing the analysis of, say, methane of the waste of ice core. So there's a lot of different pathways to lead into the kind of research that we do, but most of it comes from some sort of environmental science or earth science background.
Very cool. And one thing I think I've just been noticing through all our broadcasts today is it's such a collaborative effort. Without someone like Richard, a lot of universities and researchers across the world would not have access to these incredible resources. I mean, without the folks in the field collecting them in the first place, we wouldn't have ice cores to look at. So it sounds like there's a lot of ways to get involved in science and chime in with these amazing questions and try and come up with solutions to some of the big questions we're handling today. So on that note, I want to go ahead and say thank you, everyone who gave us your time, your questions. This was so much fun and very exciting. Thank you, Kim. Thank you, Matthew. Thank you, Asa, who are all off camera doing some of the amazing tech work to make this happen. Thank you, of course, Richard, for your time and sharing this really cool resource with us. This has been so much fun. If you want to see more, please join us again for an upcoming broadcast. We have 2 coming up relatively quickly. In fact, one is next week on March 14th with none other than Jane Goodall herself. Dr. Jane Goodall is coming to the Museum of Nature and Science, and she's going to be presenting to us virtually and talking a little bit more about actually some of these issues like climate change and how we can find hope and kind of thrive in a changing world. If you want to come back in April on the 6th, we will be visiting with the Denver Zoo, and we get to talk a bit about how they are working to save an amazing species, the boreal toad, which is native to the Colorado area. So this is very cool. We can't wait to see you again. Thank you so much, and we'll see you next time. So class, if you want to unmute, we'd love to say goodbye to you.
Say bye.
Bye.
Bye.